are going to tell us about some relatively new approaches to this problem of optimizing rate coefficients and of improving mechanisms. And there was quite a lot of discussion in these areas at the last Combustion Symposium in Warsaw last year. So some of you may well have come across some of these ideas. But this is a paper by Michael Burke, who is now at Argonne National Lab. And what he's doing here is, what this paper describes is an optimal way of trying to take experiment and theory together to recognize the uncertainties in, so these are for elementary reactions now. So he's taking experimental data for reactions, and this particular reaction here, OH plus HO2, is difficult to look at, to study experimentally, and there is some quite strange behavior being observed experimentally. And so what he's doing is he's taking together the uncertainties in the experiment and then a detailed theoretical model and the uncertainties in that theoretical model as well. So let's see what it says. Theoretical kinetics parameters with constrained uncertainties related through kinetics calculations to the temperature, pressure, m-dependent rate constants for these reactions here with propagated uncertainties, and then through physical models to combustion behavior. And so it yields a more reliable extrapolation of a limited data set limited data conditions outside the validation set. So this is a paper I very strongly recommend to you as a way of developing new ideas of the way in which we approach theory, experiment, and also statistical constraints on what we're doing in a way to understand experimental behavior for combustion applications. In that same symposium, there was a paper by Allison Tomlin on the role of sensitivity and uncertainty analysis in combustion modeling. And once again, I would strongly recommend that you have a look at this paper. So what does Allison say? Significant uncertainties exist in data used to parameterize combustion models. And that's really what we were talking about earlier on, that any of these mechanisms, especially for larger species, have associated with them significant uncertainties in the parameters that are used. The input uncertainties propagate through the models of combustion devices, leading to uncertainties in the prediction of key combustion properties. We need to focus our efforts on those parameters which drive predictive uncertainty and which may be identified through sensitivity analysis. So what that's saying is that we have a limited capability, and we ought to focus that capability on the key sensitive reactions or aspects of combustion that we identify through this sort of analysis. And Allison's paper discusses how sensitivity and uncertainty analysis can be incorporated into strategies for model improvement. So there are two things that I'd like to take from that. One of them is something that many of you are aware of, and this is sensitivity analysis. So sensitivity coefficients, and this is for flow reactors, for shock tubes, and for laminar premix flames of methanol combustion, looking at the various reactions and at their sensitivities. It's important to recognize that sensitivity analysis is of this sort is local. It's telling you about something at a particular point in the overall process, at a particular time point, under a particular set of conditions. There's a history that goes before it, which depends upon all of the species that are involved, where you're looking at the sensitivity at this particular point in time. And the sensitivity coefficient that you look at, so you're looking, for example, at something like, you might be looking at the concentration of a species, and you're looking at 1 over C dC versus, for example, 1 over K dK. So you're looking at d log C by d log K for a particular reaction and at a particular time. And so it's local. It's not a global sensitivity. And if you changed many of the parameters by a very large amount, then this local sensitivity analysis is not going to tell you a great deal. So local sensitivity analysis is particularly useful where we're we've got a relatively well-constrained mechanism. The other thing that you want to know about is the uncertainty in the overall mechanism. So what we've got is a prediction of some particular property, say an ignition delay. How is that result from the simulation? What is the uncertainty that comes from the simulation? And that uncertainty is associated, for example, with the rate parameters, with the thermodynamic parameters, etc. And so for each of the rate parameters that we're dealing with, so a particular rate constant is going to have associated with it some sort of uncertainty, a standard deviation. And so that uncertainty we can generally assume is going to be, so this is the value for the rate coefficient. This is the probability of having that particular rate coefficient. The probability distribution is usually Gaussian. By defining this standard deviation, we're essentially assuming the uncertainty distribution, the probability distribution for this rate constant across its uncertainty range corresponds to a Gaussian distribution. Now, what you do in a Monte Carlo analysis of uncertainty is to carry out a simulation, and you carry out a simulation with all of the rate coefficients selected at their optimal values to start with, but then you allow each of them to vary independently of one another across their uncertainty range. So you do a simulation in which for this particular rate coefficient, we select randomly from this distribution. So we might finish up with a rate coefficient out here. We then repeat, and then we do that for all of the rate parameters in the overall simulation. And we carry on doing it until we've got a good statistical description of what's going on. And then what we would finish up with, for example, is a value for the ignition delay, which would be associated with some standard deviation that encompasses all of those uncertainties that come from all of those rate parameters. Now, if it's a fairly complicated mechanism, then this is a very time-consuming process, because what you have to do is you have to vary all of these rate parameters across these probability distribution functions and do it a sufficient number of times to get a reasonably good statistical description. And what Allison is referring to here is what's called a screening methodology. This is what's called a Morris one-at-a-time mechanism, in which what you do is you select just a single value from this overall distribution, and you reduce the time that you take to do these calculations substantially, and you don't get an overall uncertainty. But what you do get is a global sensitivity. What the thing finishes up with is a plot of standard deviation versus absolute mean perturbation, and from varying these rate coefficients. And this plot shows you the, this is for enthalpies of formation of these species, and shows you the sensitivity of the overall result to these parameters. But this is now a global sensitivity. So what it's saying is that the uncertainty in the enthalpy of formation of this particular species here, this hydroperoxide, is by far the most important parameter. And followed by this peroxide here and so on. And then a whole string of species down here which are significantly less important. And so what you can then do with this screening analysis is that you can use that to constrain your Monte Carlo simulation. So instead of doing this for all of the rate coefficients or all of the thermodynamic parameters, you just do it for the most sensitive ones that have been selected from this global sensitivity methodology, this global screening analysis. And so I would encourage you to look at, if you're involved in this sort of process, I would encourage you to look at Allison's paper and to look up the methodology that's used in order to do this Morris analysis. Because it does speed things up enormously, because you can concentrate your efforts, your optimization efforts, or your assessment of overall uncertainty efforts on the key parameters which are identified from the screening methodology. Okay. One of the things that has been happening for the last 30, 40 years is the development of automatic methods of generating mechanisms using a computer. But it's becoming more and more feasible as the methods that are used to do it are improved. And the MIT group of Bill Green is particularly important in this area. So this is a comprehensive mechanism for butanol pyrolysis and combustion, published in Combustion and Flame, 263 species, 3381 reactions, and it was constructed using this reaction mechanism generator, which you can find on SourceForge. So this is a mechanism generator that SourceForge allows you access to it, so you can run these things for yourself. Tested against recently published data, jet-stirred reactor, mole fraction profiles, opposed flow diffusion, flame mole fraction profiles, auto-ignition delay times, doped methane, etc., etc., etc. And it's part of the overall effort in CEFRC on alcohol combustion involving these C4 compounds, various butanols. So what they do is they take the base mechanism, GRI 3.0, with nitrogen chemistry removed because they're not interested in the nitrogen chemistry. Where possible, they use published data for the rate coefficients. These are for, so they take the base mechanism and then they build on that. And as they build, they use published data for the rate coefficients for the reactions that they're adding. For some important pressure-dependent reactions, they calculate the high-pressure limit using canonical transition state theory, which we talked about, coupled with electronic structure calculations. And they, I'll show you this in a minute, they have methods available for calculating the pressure dependence. The mechanism contains reaction rate constants for 147 different pressure-dependent reaction networks, C4H9, which we'll look at in a minute, and extensive testing against experiments and sensitivity analysis. So this shows, from some of the questions that came at the end of the last session, I think I need to moderate slightly some of the things that I said because of the way in which you interpreted them. GRI-mech is an extremely useful mechanism. And the key thing about it is that you use it as it stands. You don't tune it. But it would be far from me to discourage you from actually using it under those conditions. And you can see this from the fact that this is what the green group is doing. They're using GRI-mech to get this small chemistry. Remember this hierarchical approach that we talked about. Much of the chemistry is driven by the small molecule chemistry, hydrogen, oxygen, methane chemistry, etc. And that's what GRI-mech does very well. The bigger molecules, what happens with the bigger molecules is that they, especially for very big molecules, is that they fragment and form smaller species. And these smaller species are then described, their oxidation chemistry is described well by these small molecule chemical mechanisms. But what Bill Green is doing here is extending this in an automatic way to include some of these somewhat larger species. So this is still small. This is C4 chemistry. So this is the butyl radical. And so just what can happen to a butyl radical? If I draw that, does everybody understand what I mean? Do the fluid dynamicists understand what I mean by drawing that? You're not happy with that? Let me do it in full. So if we take, so we've got CH3, CH2, CH2, CH2. That's the one butyl radical. And one of the things that it can do is it can isomerize by transferring a hydrogen atom from here to here. So it forms CH3, CH2, CH with the radical center there, and CH3. And that occurs really quite quickly. So this is the lowest energy process that, in which the butyl radical is involved. And then what can happen is you can get fragmentations of these species. So for example, this species here, it can break this bond here and produce an ethyl radical plus C2H4, or it can lose one of these hydrogen atoms here and produce CH3, CH2, CH, CH2 plus H. And that's a higher energy process, but both of them are feasible. And so what you do within an automatic mechanism generating process is you automatically incorporate these types of reactions. So you have a protocol in which you tell your computer that if it comes across a butyl radical, which it will recognize from a structure that you give it within the program, when it comes across this species, what it will do is allow it to undergo these three reactions. This isomerization to form this radical, which can fragment in various ways, this carbon-carbon bond scission, and this reaction here, which leads to the alkene plus H. And associated with each of these, there will be rate parameters. And for these particular radicals, those rate parameters are known from experiment. For some species, they're not known from experiment, and so they would be estimated. And ideally, they would be estimated using transition state theory coupled with electronic structure calculations. Okay, and so this shows a reaction pathway analysis for butanol. So this is the mechanism that the computer has generated for butanol. And so what we've got here is the butanol in the middle. The heavy lines are the heavier the line, the more probable that particular reaction process is. And so here what we've got is a hydrogen atom reacting and abstracting a hydrogen from this carbon here. And that carbon-hydrogen bond is the weakest hydrogen bond in butanol because of the effects of this OH group there. And that's well understood and well characterized. And so at this particular temperature at which this simulation is done, something like 25% of the reaction is going through abstraction to form this species here, which then goes on and reacts with hydrogen atom. Then what this does is it dissociates, generating a hydrogen atom, losing a hydrogen from here, and producing this aldehyde. And so on throughout the whole reaction network. And so those reactions are understood. We understand that those are the reactions that are likely to take place. What Bill's group does is put them into this reaction mechanism generator, says that these are the reactions that will occur for this particular structure with these particular rate constants, and generates the reactions. And then he moves down from each of the initially generated radicals and allows them to react, again, using a protocol which recognizes the way in which those reactions will occur. And the great thing about this is that it happens very, very quickly. Once you've built the reaction mechanism generator, then you can generate these mechanisms very, very quickly indeed, and then go on and test them. And you can also do experiments with them. You can test various issues associated with the rate data that you're putting in there.
So for that one, the 10%?
Sorry?
I see everyone has like 12%.
Yeah, so for this particular set of conditions, what the rate data that goes into the mechanism tells you is that at this particular temperature, 8% of the reactions between hydrogen or CH3 and butanol take this hydrogen atom here off and generate this oxyradical here. 18% takes this hydrogen off and generates that radical. 17% take this hydrogen off and generate that radical. So these are the results of the simulation that you do using this mechanism, and this is then an analysis of the reaction pathway from that.
So this number is calculated
by the simulation. Yeah. So.
Is this increase over the entire time of the reaction, or is it just particular time snapshot?
This will be necessarily a time snapshot. So it's dependent, obviously, on the relative concentrations of H and CH3. Okay, and the other thing that he does is he can estimate automatically pressure-dependent rate coefficients for parameters. And this is done using a master equation methodology. And he has methods of it. The calculations depend upon the densities of states of the species in the network. And he has methods for calculating those densities of states, all built into this automatic reaction mechanism generator. And then methods of simplifying the full master equation model to get a single set of phenomenological rates. One of the things that we did was we said that what we want out of this, the master equation methodology gives you eigenvalues, but what we actually want are rate coefficients. And so the RMG has ways of estimating these rate coefficients. There's arguments about the validity of the approach that's used, but it's a pretty good methodology because it's fast and it is providing a very practical approach to difficult problems, because what it allows you to do is on the basis of pretty good science to estimate many of these rate coefficients, to generate the mechanism and then test that mechanism against observations. So what's the take-home message from this lecture? I suppose it's that there are many mechanisms out there. Some of them are better than others, and you need to be aware of what's going on. So you need to be in touch with the field. Don't just pick up any old mechanism and use it. You've got to know something about the provenance of the mechanisms that you're using. And undoubtedly, despite its flaws, GRI mech is a good description for small hydrocarbon chemistry. The hydrogen-oxygen mechanism is pretty well defined and is getting better and better and better because the reactions that are involved in it are reasonably simple, and they're amenable to both an experimental and a theoretical approach. And so hydrogen-oxygen is in good shape. For these larger species, then there is going to be a lot of development over the coming years. That development one contribution to it could come from this automatic mechanism generation approach that Bill Green is producing. Another thing that's important is understanding. These mechanisms are going to be pretty complicated, and we need to understand the ways in which they're going to be used and what are the key processes that are involved. And so sensitivity analysis, local sensitivity analysis, global sensitivity analysis, and global uncertainty analysis are really essential processes. What I haven't mentioned, as I said earlier on, is that I haven't said anything about mechanism reduction or lumping. And if you go to the combustion symposia over the last several years, you'll find that there are sessions which are devoted to reduction and lumping. And that's a good way of getting an insight into the approaches that are used if you don't have any background in that area. Okay, any questions? Yeah.
So we see if we use mass equation, we don't care the detail of the inertial reaction. We just care the main reaction channel, the main product. Is that correct?
As a combustion person interested in constructing mechanisms, we're interested in the phenomenological reactions. So we're not interested in the rates of energy relaxation. We're interested in what the reactions are, what the products are, and the rate coefficients leading to those products. It's essential, though, if we're taking results from master equation mechanisms, that we understand what's going on. So it is, I think, it is a requirement of us that we have some understanding of what's gone into the generation of those rate coefficients. I was in Hefei in China 2 weeks ago, and we were talking about a particular set of calculations using master equation approach, in which the basic understanding of what was going on had been lost. And so what they were doing was they were generating rate coefficients, but not really using the full phenomenological model that was required. So you need to have an understanding. But in the end, it's the rate coefficients that we want and the products that they lead to.
Question. So, what's your assessment on how will the accuracy of digital models in future for larger hydrocarbons going to affect the analysis of real combustor systems? So, how much accuracy do we need to aim for when we are going to diesel, jet engine fuel, and stuff like that?
Yeah. As I Ron can contribute to this conversation. We were talking about this at breakfast this morning. One of the interesting issues is that if you take a large alkane, dodecane, then that's going to generate a lot of radicals directly from itself, just by breaking CC bonds, by breaking CH bonds. In something like a jet engine, then that's going to occur very quickly. And it's going to be far faster than the rates of reaction with oxygen. So we don't need to know about the chemistry of these large fragments with oxygen, because what's going to happen is they're going to fall apart. And they're going to generate small species. And so quite rapidly, you're going to go from this large species, and you're going to produce a set of small radical fragments. And it's the oxidation of those small radical fragments that's important. And is that a fair comment, Ron? And so what you need to understand is the pyrolysis of these large species. And that's an awful lot easier than the oxidation chemistry. It's still complicated, but that's... and so that, in many ways, simplifies the problem and says that in terms of oxidation chemistry, we need to understand the small species, the smaller species, these C1s, C4s, etc. And the larger species are going to fall apart. And this is advantageous in many ways, because that falling apart process is pretty complicated, because if you look at it from a master equation point of view, there's an overlap between the eigenvalues associated with chemistry and the energy relaxation eigenvalues. And so describing it kinetically is quite difficult. But all we need to know are the overall timescales and the products. And so that simplifies things quite a lot.
I have a related question. So as we start generating larger and larger mechanisms, I wonder what the end game is, considering that simulations typically scale with the number of species squared, and already we have mechanisms that have 300, 400 species in them. What's going to happen when we need to start describing these larger fields?
Yeah. I think that there are two aspects to this. One of them is that what we understand at a fundamental level is elementary reactions. So we understand elementary reactions reasonably well. We don't always get the answers right, but we understand them reasonably well, and we have ways of determining the rate coefficients, both theoretically and experimentally. And so I think that it is incumbent upon us to use this approach overall, but to focus on what are the key reactions. So, for example, with that large alkane, we don't need to worry about the oxidation chemistry of these large species. We just need to know about what their products are going to be in the timescales of that overall reaction. So we, to somebody who's interested in chemical reactions, there's a temptation to say, oh, well, let's go and have a look at this reaction. But we kineticists should be focusing our attention on what are the key reactions. Okay? And we get to know about what are those key reactions by constructing the mechanisms and then doing the simulations. But those mechanisms necessarily are these big, complex mechanisms. When you've done that, what you can begin to do is to reduce the size of the mechanisms. And so if you're going to put this stuff into a fluid dynamic code, then it's got to be simpler than the stuff that we give you. But there is a huge industry of people who are developing understanding of the ways in which these reduction methodologies, these lumping methodologies work. So Mass in Germany, Stephen Pope in the US, these are people who have developed a range of approaches to understanding these things occur. And this timescale analysis, for example, is one of the central processes of central parts of what's going on. And so, I mean, that's one of the beauties of this subject, that it has so many aspects to it. In the end, what you want to do is you want to simulate an engine or something. But there's a lot that goes into that process. And the last thing that we want to have is a chemical mechanism used in a really nice fluid dynamic code that is rubbish. You know, it's got to be a decent mechanism. It's got to be small, but it's got to be a good mechanism. It's got to be tailored to produce what's needed in the simulation. And I would argue, from a biased point of view, that ultimately that's got to be based on sound science, sound understanding of the elementary reactions that form a part of that overall mechanism, a sensitivity analysis, global uncertainty analysis, and then to get to the fine, and a testing of that mechanism against experimental data. The evaluation of the mechanism is essential. Once you've got that good mechanism, you can lump it, reduce it. That's hard, but it's possible to do. And again, you can test against the full mechanism and test against the experimental observation. So I think that's the philosophy that I would argue you need to use. The last thing one wants is, I would say, is to say, okay, here's a complicated combustion system. Let's produce a nice small mechanism out of our heads. That's not a fundamentally based approach, and in combustion we ought to be fundamentally based. Yeah.
So it strikes me that it seems there's in a way two approaches that we've discussed here. Where one is you build a large mechanism, say like GRIMEC or something like that, and then you have all these reactions and you reduce it to kind of apply to your own situation. Or you have something like RMG or Prime, which are actually now connected, I believe, like you can use them together, where you start with your initial conditions and you build the mechanism from there. So one, you're starting small and building, and one, you're starting large and reducing. Could you comment on which one of those, if that's an accurate way to talk about it, and which one of those would be more?
Yeah, I wouldn't say that RMG, I mean, RMG is based on fundamental elementary reaction kinetics.
Right.
You know, it's not constructing a tailor-made small mechanism. It's actually constructing a big mechanism.
Right, but it's more. I guess I'm not saying that you're. I mean, they're both based on elementary reactions.
Yes. Yes.
Absolutely, and they're both drawing from the same repository, which is GRMEC or just a big amount of reactions. But it seems that RMG is building you a mechanism from your initial conditions, whereas a more classical approach is to reduce a large mechanism to your own set of conditions.
No, I wouldn't agree. I wouldn't agree with that. I think we could argue for some time, but I mean, I think there is intrinsically no difference that I see between RMG and a classical way of constructing a chemical mechanism. The great thing about it is that it's automatic, but it's still based on this whole set of reactions. I mean, if you're building it for butanol, then you build it for butanol, and I think that's maybe what you're saying, that you don't take something that's been written for a wide range of fuels and use that. You actually start off with the fuel that you're interested in and build the reaction mechanism from that.
Right.
But essentially, I think the approaches are identical. I mean, they're not identical in terms of implementation because RMG is so much faster. RMG, if anything, will produce a bigger mechanism than some of these other so-called elementary reaction mechanisms that we're talking about. I don't know. That would be my argument. Yeah.
At National Combustion meeting this year, James Opelin from Sandia talked a lot big mechanisms and these big simulations, it's not even as much about fluids or chemistry. It's now a computer science problem of developing like efficient algorithms. Do you think like a lot of this is we could use a large mechanism, but just the computation isn't there yet?
Let me give you an example from atmospheric chemistry. We have a mechanism that consists of 5,000 species and 15,000 reactions. That's pretty big. There is a group in California that have used that within a regional atmospheric model. That's with full transport. I mean, transport is somewhat simpler in the atmosphere than it is in a combustion system, but the region that you cover is large. So it's essentially the same sort of problem that you're using a grid and you're solving the rate equations on every single one of those points. And so they were able to use this absolutely huge chemical mechanism. And in a way, it is a question of computer power. But there is another issue, and that is understanding. If you have a mechanism that contains 5,000 species, then you look at the final result, but you don't get a lot of understanding on the way there. Or another way of putting it is you have to do a lot of work to get that understanding by looking at the species that are involved. And so one of the advantages of this overall approach that I've said of taking the big mechanism, testing it, evaluating it, reducing and lumping it so that it can go easily into a CFD code, you retain a lot of essential elements of the chemistry in a lumped form, and in a way that's often easier to understand than if you retained the whole of the chemistry. So I mean, I think undoubtedly, as computer power increases, and it's a phenomenal rate of increase, that we will be able to use some of these big mechanisms directly. But there's a lot of redundant chemistry that's in there, and there are advantages in taking this reduction and lumping approach because the methodologies have been developed, and you may as well have as efficient a calculation, provided it's accurate, as you can get. Any other questions on this?
Is it, I mean, we're defining all these mechanisms in terms of each individual elementary reaction, right? And is it possible that one day, like, we can describe each reaction perfectly for every system? Like let me see if I can phrase that in a more lucid way. Say you take H plus HO2 goes to OH plus OH. Is there a way that in the future we could just have a set of parameters for that reaction that describe it perfectly for any system? Or do we always have to go back and reevaluate how we define each reaction?
No, I think H plus HO2, I think I think could be defined very, very accurately using a combination of experiment and theory even now. So you could get to a situation where H plus HO2 is a solved problem. We can forget about it. We just put those parameters in. In addition, when you're doing, there's an interesting issue about what you're doing when you're doing an evaluation of a chemical mechanism. What you're doing is you're evaluating how well that chemical mechanism is describing the whole system. And you then do a sensitivity analysis of whatever sort, which tells you something about the sensitive parameters that are involved, and which might tell you, oh, look, this reaction is highly sensitive, or the system is highly sensitive to this reaction. And the rate parameters are not well defined. This is a good system to go away and improve our understanding of. What I don't think you should do is to say, that's the most sensitive parameter in this system. if I tune it to this value, that's going to give me a better value. You've got to be very careful about doing that. I mean, this, in a sense, is what one might be seduced by the approaches of Thomas Durrani and Hai Wang into thinking that that is a good approach. But you've got to remember what they're doing, and they're doing things extremely carefully in a very statistically constrained way. And what they're actually doing is not, by and large, tuning the parameters. They're reducing the lack of precision. They're reducing uncertainty on the parameters rather than anything else. And so, as an elementary reaction practitioner, I'm, in a sense, beating my own drum here. But what we should do from that process is go back and evaluate and look at the elementary reactions directly and improve them and then put them back in the mechanism.
So you think at one point there could be, like, just maybe like you said, we've solved that problem. Like, we go about systematically solving each elementary reaction in a way, like using these example systems,
Yeah.
which are of interest
Well,
to us. And then eventually, it's basically like I don't know, a good metaphor might be Legos. You have each puzzle piece which you can build into your own little house.
Well, I mean, I think we are very close to solving the hydrogen-oxygen problem. You know, a lot of those rate data are now really very well defined. The way in which they interact is very well defined. We can improve on the precision, but and people will continue to do so. But for more complicated systems, I think we're some way away from which is good. Okay. After coffee, what we're going to do is we're going to talk about nitrogen oxide chemistry. But there was a question that was raised yesterday that I'd like to go through because it's important in understanding one of the reactions that we're going to talk about. And what we talked about was methylene chemistry. And we talked about singlet methylene and triplet methylene. And from the reaction that I got, not everybody understands not everybody understood what I was talking about. So just let's see what's going on here, because we'll use it with nitrogen chemistry. So if we take methane, then each of these bonds here has got a couple of electrons associated with it, and those electrons have got spin. So each electron has got a spin with it, which we describe by a little s, and it's given a quantum number 1/2. And that quantum number of 1/2 means that it can point in one of two directions. So we can think of this electron as either pointing in that direction or pointing in that direction. Now, when we form methylene, what we do is we break these bonds here, and we produce two hydrogen atoms, each with an odd electron, and CH2 with 2 electrons. And this molecule, methylene, has got a number of what are called orbitals where these electrons can go. And they can be arranged in 2 ways. They can be arranged either with both of their spins up or with one up and one down. And what we can do is we can describe the total spin of these systems. And here, those two spins are reinforcing one another. They're both spin up. And so the total spin, which is given a symbol capital S, is equal to 1/2 plus 1/2, which is 1. And in this case, the total spin is S is equal to 0. Okay? Now, One of the problems is that in spectroscopy, we are very much influenced by the work that went on over a century ago before people understood what was going on here. And what they used was a certain terminology which describes essentially this. And they used a quantity which is called the multiplicity. And the multiplicity is equal to 2s plus 1. So they did this because that allowed them to describe the energy levels of the system. But it's made life a little bit more complicated for us because we describe the atoms or the molecules in terms of the multiplicity itself rather than in terms of these of the spin. And so in these cases, the multiplicity is going to be, so if we write down the multiplicity here, the multiplicity is going to be 2 times 1 plus 1, which is 3. And in this case, the multiplicity is going to be 2 times 0 plus 1, which is 1. And we call this a triplet and this a singlet. And it's called a triplet because there were 3 energy levels associated with this system, with these sorts of systems. Okay, so when we look at methylene, then what we've got is we've got an excited state in which the electrons are paired like this. So clearly S is equal to 0, and the multiplicity is equal to 1. So it's a singlet state. And then we've got a ground state, which is 9 kcal per mole lower energy. And there, the spins are arranged parallel. So S is equal to 1. The multiplicity is 3. And this is called a triplet. And one key issue that pervades methylene chemistry and is also important in nitrogen chemistry, which we'll talk about in a minute, after the break, is that a transition with delta S not equal to 0 is very slow. So remember, the spin is S. So what this means is that going from a triplet to a singlet, or back again, is a very slow process. It's what's called a spin disallowed process. And that's a key thing in methylene chemistry. If you remember, we just had a few energy levels which were perturbed and mixed singlet and triplet. So it does happen, but it's slow. And when we talk about the chemistry of nitrogen later on today, then again we'll invoke these ideas that these singlet triplet processes, or processes with delta S not equal to 0, are very slow. So generally speaking, spin is conserved in reactions involving these small species. Okay, let's break there, and then we'll come back in a quarter of an hour's time and do the nitrogen chemistry.